Good morning. My name is Jose Lorenzo. I am working for for Atos in Madrid, and I'm the coordinator of the Candela project. And I welcome you all to this second webinar of the series of 5 as a preparation of the hackathon that we plan at the beginning of November in Frascati. Candela, the same as the other 4 projects involved in this hackathon, has been funded by the European Commission in a call some months ago, already almost 2 years, around big data and Earth observation. So the objectives of the projects are at some extent very similar, but the applications and the focus of the research, as you will see, is put on different topics. I will count today with some of my colleagues in the project. So you can see now how we have structured the webinar. I hope the shift between the different presentations is okay and makes the presentation smooth. So I will take a few minutes, I hope not more than 5, on a very brief introduction to the project objectives. And then we really will focus on the presentation on the technical aspects of the project, as I said, as a preparation of what you could expect in Frascati, and the tools that you will be able to play with during the hackathon. We organized the presentation around the 4 main tools which are subject in the Candela project. But before that, my colleague Hugo from Atos France will give you an overview of what has been already deployed in the Candela platform, which basically is done in the Cloudflare environment, which is shared with the Creo Dias. So you will be able to see how we plan to give you access to the resources. Basically, what we do in Candela is to try to encapsulate most of the tools which are being implemented as Docker containers, and these deploy in the platform and being accessible in a very similar way as some of the things that you have seen from OpenIO through notebooks in using Jupyter Notebook. So after the platform introduction, we will go through the tools on change detection, both on optical and SAR data. Then we will focus on the data mining and data fusion tools. And last but not least, we will have a quick look to what is available already as part of the semantic search and indexation building block. So let me somehow justifying the structure of the hackathon. Again, the focus of Candela is, or the objective, the high-level objective is to allow users accessing and analyzing large volume of Earth observation data around 4 main applications. As I said before, data mining and data fusion tools, work which is driven mostly by DLR in the Candela consortium. Then we have specific tasks on change detection on Earth observation time series, both for optical data, activity who is led mainly from Thales Alenia Space in France, and for radio data activity which is led by Thales colleagues, but this time from Italy. The main work around semantics is led by IRID, the institution dependent on from CNRS, also in France, and our colleague Bawi will give you a quick overview on what will be available in terms of semantic search and indexation at the hackathon in Frascati. Again, all these tools, most of them are encapsulated as a Docker containers and are available at the platform, and hopefully you will be able to play with them during the hackathon. The applications which have been integrated in the platform and have been adapted to the two main use cases which are used in the project as a proof of concept. So the data sets and the tools has been somehow customized for the agriculture and forestry domains. We count in the project with basically two cases in the case of agriculture and another two for forest monitoring, which basically help us to validate and to test the tools which are implemented in the project. Therefore, the examples that you will see and the data sets that are now used by the project partners to validate the tools are mainly in these two areas. So regarding agriculture, focusing on analyzing the impact in urban expansion in agricultural land, and also estimating the effects of natural hazards like could be frost on vineyards. The second area of validation, as I said, is forest health monitoring, basically by using two main sub-use cases. One focusing on the effects of caused by natural disasters, and a second one on forest health monitoring. But again, you will have, I will show you later the different resources from the project website, and in our Twitter account, where you can get more information from the specificalities of the use cases. By the way, all the public deliverables which are released by the project are as soon as provided to the Commission also made available in our project website. So you will have already access to the requirements which have been expressed by the use cases and where we based our implementation. But my idea is not taking more time on those generic things, which can be any case at the end of the presentation. If you want more information, we can take part as part of the questions. But given the floor to the colleagues, which will go more on the technical details, which I think is the useful information as a preparation for the hackathon. So I will try to give now the floor to my colleague Hugo Lopez from Atos France, who will make you the quick overview to the platform and the way that we plan to provide access to the project resources during the exercise. So let me try to make Hugo as presenter. I hope Hugo can now already share his screen, and if he unmutes, probably also take the word. Hugo, can I hope? Okay.
Yes. So let me. Oh, I'm gonna show. So you should see my screen now.
Yes.
This is the wrong point. This one. Good. Okay, so I'm gonna talk about the actual CANDELA platform. So mainly focused on how to use it, so that you have some information before the hackathon. So let me full screen presentation. So first thing, I will tell you how to connect to your Jupyter notebook. Here. So the participants of the hackathon will have to provide their mail, first name and last name, so that we can create an account on the Candela platform. A username and a temporary password will be communicated to any participant, and then you will be able, when the hackathon will start, to connect to its Jupyter notebook at the address platform.candelah2020.eu/hub. So at first sign on, you will have to enter your to authenticate with your temporary username and password. Then you will be asked to renew your password, and then you will have to choose between two options, and you will choose the Geoscience Jupyter Lab notebook, which is a basic Jupyter notebook with useful visualization tools like Leaflet to get started on your work. So the Jupyter notebook has the form you can see here. So at the user root folder, you have 3 folders. A library folder containing the sources of the library we developed for Candela. A public folder then, which contains examples. This folder is read-only, and you will have your personal workspace called work. So you must work in the work folder, as it is the only persistent folder where you can execute scripts or notebooks. We plan to create an exchange folder so that you can easily share amongst users scripts or data between users of participants of the hackathon. So that being said, you have 2 very useful features in these notebooks. So you have Python 3 notebooks, so that you can execute code, and also terminal windows, where you can do operation in Unix Unix-like style. So basically, it's a terminal in a CentOS container. So from there, you can copy a thing and do operations with some control, like zip folders or copy paste easily. So then I'm gonna present the Python notebooks by themselves. So as you see, the notebooks are a series of cells where you can execute, that can be executed. It works like Python console. So any cell executed runs into a kernel, which is basically an opened Python session, and you can print where you can do whatever. So, and the result is displayed under the cell that you run. So here is an example, very simple, where I print just a string and import some library to see where the Python script is executed. So you discover that the root folder of your notebook is Om Jovian. So this might be an useful information when you will have to think about absolute or relative things. But you'll see that later. So what's in the Python environment of the notebook? So for Candela, we developed two useful libraries. The first is a CRIODIAS data connector that allow you to retrieve Sentinel, Landsat, and VSAT, all kind of data from those collections, and search in these collections the data you want to use, as well as retrieving the data. We will see that later in details. And we also have a WPS library that allow for launching WPS processing developed by the partners on our Candela cloud. On top of these custom libraries, you have the usual libraries for geographical data treatment like rasterio, netcdf4, numpy, scipy, pandas, and you can add whatever library you want using conda or pipe, as you have from the terminal access to conda, and you have the rights on it. So you will be able to add any library you want during the hackathon. So at last, I'm gonna show you a demo of the CRIODIAS connector. So that it's the library we developed, and that allows you to search data, geographical data in the catalog of CRIODIAS. So you see here the list of available data. So in VSAT, JSON, Landsat, Sentinel, 1 to 5. And with that, you can search, filter, and get a link to the data. So let me show you that. Okay, so you should see now my my Jupyter notebook. So I created a script in my work folder for this demo. So I'm launching the Python notebook. The kernel has started, and I'm gonna run the script and comment what it's doing. So first I import the CRIODIAS library. Then I'm gonna show you the list of parameters on which you can search, over which you can search data. So amongst other, you can select bounding box. You can select the type of satellite you want, the type of instrument, the resolution, and a lot of other things. So Here I'm going to search Sentinel-2 image containing such bounding box from the 1st January of 2018 to the 1st of July 2018. So it connects to the QDS catalog and returns the results, 300 results. So you can do filter operation. Here I'm gonna filter to have products that contains those are regular expression. I'm gonna select filter. I'm gonna select product that contains well, that are I'm gonna select basically one product per month at the start of the month by using the pattern, the date pattern in their ID. And well, I have now a subset of products which starts which are taken at the beginning of the month. So I'm gonna make a search, a more specific search over Toulouse with a little cloud cover on Sentinel-2 level 2A processing level during the month of May. So I only have one result. I displayed the identifier. As you see, it looks like an URI, and I'm gonna create a link from this URI. It's the storage where the data is on the CANDELA platform to my workspace. So I'm gonna create a link for this set of results, which has one element, into the link folder in the current folder. So it creates the folder, and here I have my data, and it's the Sentinel-2 level A classical folder organization, and here I have all my bands with all resolution, and can work on. And from there, you can work with the data. You just made available to your Jupyter notebook and work environment. So I'm done here. I'm gonna let the floor to.
Okay, thank you, Hugo. Well, you will see this was an example of how to interact with the Jupyter Notebook at the platform. During the presentations of the different tools by my colleagues, you will see already, since this is done from different notebooks, more ways to interact with the tools through the Jupyter Notebook. I will take again the floor, I hope. Okay, what I will do is to, if Andres allow me, since Michele it seems to have to leave early, we will shift a little bit. We were intended now to present the change detection on optical data, but we will start with the SAR part by Michele. And we will continue with Andres. So Michele, I will give you the floor now, so you can share your screen and go ahead with your slides.
Okay. Can you see it?
Yes, I do.
Okay. Sorry about that, but there was an emergency here, so I have to leave early. So we developed a search detection building block, which is completely automatic and operates on Sentinel-1 interferometric wide swath ground range detected images. And it's based on a neural network operating in the spectral domain for an experimental approach. Our tool is made of two modules: a preprocessing module which takes the standard safe format Sentinel-1 images in dual pole BB and BH, as it's the one covering most of Europe and the central area of the world. So, and it performs radiometric calibrations and terrain correction, and then saves the results in JOTIF format. The user can either input a region of interest as latitude and longitude of the interested area, or leave the preprocessing module to detect the overlapping area between the selected products and extract it automatically. Then we have the actual change detection module, which takes the results of the preprocessing and perform change detection on the time series pair, saving the output in JOTIF formats again. Here is a representation of the pipeline. So the actual change detections, as I said, operates in the spectral domain with a multi-layer perceptron network, which takes as inputs statistics from the spectrum of the images. It's a patch-based analysis, so each image is divided in 10 by 10 pixel tiles, and then each tile is analyzed individually. The results is a false color change detection map in which changed areas are highlighted in red, and metadata containing geospatial information about the acquisition and the percentage of changed and unchanged tiles is reported. Sorry. For training the network, we developed a data augmentation algorithm which takes original SAR images, Sentinel images, of course, and generates time series by adding or removing scattering elements or emulating signal fluctuation in clutter or major scattering by additive Gaussian noise based on the scattering statistics of the images itself. This allows us to automatically label each generated pair and then train a bucket of models using a set of hyperparameters to build and train all the possible combination of networks, and then select the most accurate one based on the results on the test set, which is made of 20% of the total generated pairs. So I will now share a quick video to show you how to search the products within the Jupyter Notebook and run the whole pipe. So here we are looking for Sentinel-1 products on to-dos. The geometry is the GRD product, and we also inputted a start date and the completion date for the interest time interval. We then proceed to show the number and the list of the products that were found. And for the sake of simplicity, we chose the first and the last in the list. So we then create links to those products and input the latitude and longitude of our region of interest. This will create a box which will also speed up the whole process. Otherwise, we will have to process the whole image, which is very big and will take a lot of time. We're launching the preprocessing, and when it's done, you will see JOTIS in the preprocessed results folder along with a log text file. Once it's done, we can then launch our change detection. So here on the left are the results of the preprocessing. We selected 2 products in dual poll, so we have 4 results, and we have the log files as well. Once the change detection is done, in the change detection results folder, here on the left, you will see the actual change detection map. Right now, at this stage in the processing, just the BV polarization was done. And there's also a log file which will show the processing time and just give you a hint of when the processing is done. And that's all for me. And sorry if this was quick, but there was an emergency at the company and I actually have to leave. If you have any questions for this part, feel free to ask, I don't know, Jose or anyone else from Candela for my email address, and I will answer by mail. And I will, at this point, I don't know, Jose, I will give you the presentation to you, to Andrea.
I will take it. Thank you, Michele. In any case, the same as with opening your presentation, the webinars will be made available, and of course we will take the questions from now until the hackathon or the day of the hackathon itself, if anyone wants to request any additional information what we have just introduced today. Okay.
Okay.
So
thank you, everyone. Bye.
Thank you, Michele. So now I will give the floor to Andres. Andres, if you can unmute.
Yes,
okay.
I'm here.
Okay. In this case, I will be showing the slides in a similar way as Michele was doing. The speech will be given by Andres. So please tell me when you want to shift from one slide to the other in order for me to keep your
Perfect, thank
speech. Okay.
Okay, so Andres Troya from Thales Alenia Space, France, and I will going to present you the change detection pipeline on optical Sentinel-2 images. So in the slide currently on the screen, we see the global architecture of the pipeline, which starts from raw Sentinel-2 data products, which are then transformed by one function into GeoTIFF images, which are easier to process by our algorithms. Then we use another module to actually split the tiles so that they are easily processed by many nodes in the CANDELA platform via Docker containers. Then the actual change detection module, which is going to apply some deep learning algorithms to compute the changes between pairs of co-registered images. And finally, one module which is simply doing the merge of the sub results produced by previous steps in order to recover a whole change detection map on the initial area of interest. So you can change the slide. So now I'm going to give a quick overview of the inputs and outputs of each module. So the JPEG-to-TIFF module takes as inputs principally a folder, which is the path containing a set of different Sentinel-2 raw products, and an output folder, which is the folder in which the resulting GeoTIFF are going to be written. You can also pass as an option a list of the bands that you are interested in. So we are not limited to RGB or RGB NIR. You can pass any combination of bands that you are interested in, as well as a Boolean mask. If you have some kind of classification or something that allows you to really focus on the area of interest for your application. Then, as a result, the corresponding geotiff as well as the masks associated to your data are written in the output folder. You can change the slide, Jose. Okay, so the split image module is just a simple preprocessing step, which is going to take the a folder path where you store the geotiff that you are going to process, and you give the number of splits that you want. This number you should compute it by yourself in function of the processing power of the available resources. And as a result, a JSON file is going to be written, which contains the different sets of core registers images that are actually in the folder that you provided, as well as the best way to split the actual images as horizontal bands, sub images to be processed. Then the main module, change detection, will also take as input, as always, a path in which you put all of your geotiff images, the output path where the results are going to be written, and then there is a list of the images, the coordinates that are provided by the split image function, as well as some other options to normalize or to mask the change detection, and the encoder that you're going to use. This encoder is the path to a deep learning model, which is trained offline. So actually, there are some pre-trained models that can be used for testing on Sentinel data. And in a future version, we're going to provide also a module that will allow the user to train models by himself, maybe to specialize on some particular area to obtain better results, maybe. And the result is just the sub image, or maybe the whole image if you didn't make a split before, containing the change detection map between 0 for no change and 1 where there is a very highly likely change. The last there's a little mistake in the name of the last module, which is just the merging module, which will take the path where all of the sub results from change detection were written, and which will just concatenate all of these sub results into a complete change detection map. So now I can show you a little video showing this whole processing pipeline on the platform. So what we see now is a Jupyter notebook on the platform, in which we created a script that is going to go through all this pipeline. So the first step is actually to utilize the CreoDS library in order to find the data of interest. So what we can provide with this search and link function is the Sentinel-2 collection the bounding box of the region of interest, the dates that we're interested in, and a folder in which all of the symbolic links to the actual data is going to be created. So it should be created in your local work directory. And so when we execute this, all of the functions that were described by Hugo before are done automatically to recover and create links for all of the relevant Sentinel-2 folders in your workspace, as we saw there. Then we can just delete the links potentially when we're finished, and then we created one little module called pipe, which encapsulates the calls for the different steps in the pipeline. So the first one is the JPEG to TIFF, to which we provide the links directory that we just got from the research function with CreoDS library. And we tell it to write the TIFFs in a new folder, which is called TIFF, for instance, and we are going to get bands 2, 3, 4, and 8, which are RGB and near infrared bands. So this is executed, and after a little bit of processing, we get the results in the TIFF folder. So we have the actual GeoTIFF, as well as some masks that are associated with this GeoTIFF. This mask contains the cloud mask, which are available from the raw products, as well as some processing logs to see if everything was okay or if there were some errors during the execution of the module. Next, we call the split image module, which was called in this script preprocess, but it's the same. So we tell it to preprocess all of the TIFFs that are in the TIFFs folder, and to write the results in the same folder. And we would like to make three splits. So each Sentinel-2 image is going to be splitted in 3 horizontal bands, which are more or less of equal size, modulo some remain at the end of the tile. So we do this, and it's going to create a single dataset.json file, which contain actually different keys. So this 1 and 2 keys corresponds to 2 different tiles that are co-registered. So in the first one, we have 6 images that correspond to this area, and the coords property is going to give us how to split the tile for the processing. Then to execute the change detection workflow, we give him again the TIFFs folder with all of our GeoTIFF, a new folder which we call result, in which the change detection maps are going to be written at the end of the processing. We should pass also this JSON file that we created before, so that the jobs can be actually distributed on the processing cluster, as well as the model, which is available. And as you can see here, there are 6 or 7 pre-trained models that you can use for now. Okay, you execute this step is actually quite computing demanding, so it takes a while to process everything. But here we just skipped for the video, and then we obtained like the sub results for every pair of images, which are then merged by the final module, which is the merge results function. And after this execution, we will get for each pair of images a single change detection map, which we can then analyze and process further in the Jupyter notebook, for example. Also, I think that Hugo didn't show this before, but there is one visualization plugin that is going to it's being developed to actually visualize the results in a nicely done plugin on the Jupyter using Leaflet. So this is all for me. If you have any questions.
Well, I think we will take the questions probably better at the end, Andres, also
Okay.
depending on the time that we have available, since we still have the talk from Mihai and from Bowie on the remaining things. Thank you,
Right.
Andres.
Okay, thank you.
I will give the floor now to Mihai. Mihai, can you hear me? So
yes,
I will make you. Okay, I will make you a presenter, so you can take control over the screen, so you can directly show your slides. Okay, Mihai?
Yes. Can you see the slides?
Yes.
Okay. Second. No. So my name is Mihai Datku from the German Aerospace Center DLR in Oberpfaffenhofen. In CANDELA at DLR, we have the task on data mining, data fusion, and also on the data science workflow. So in CANDELA, we paid, the project CANDELA paid special attention to reuse, adapt, grow, further develop existing solution, which have been demonstrated in large applications. And in this line, we continue our development of the data mining tools, which have been installed in the ground segment of TerraSAR-X, the German satellite. So in the project, we further develop these tools, adapt them to Sentinel-1 and Sentinel-2, and we edit the data fusion, which is a specific operation in CANDELA. So that is, let's say, the main workflow and presentation of the analytical tools. So actually in CANDELA, we have on the left side the data sources, which are Earth observation, Sentinel data, and non-Earth observation data. From the Earth observation data, our task is actually to process them via data mining, data fusion, and generate semantic labels. The labels they are later jointly analyzed with non-aero data, which is the next presentation from the CANDELA project. So that is a basic architecture for the data mining and data fusion in CANDELA. So on the bottom part, we have the ingestion, the processing of the satellite Earth observation products. This means mainly tiling and extracting the features. The features and the metadata, they are stored in a data mining database management system. In the middle, the orange database. That is an actionable database with a property that's the design as a relation database allows very fast access. I mean, seconds for operation of machine learning. And this actionable information database measurement system, it is operated by tools like acknowledge search, annotation, semantic, which are implementing the function on data mining and data fusion. So for an understanding of the module, in here we take the metadata, we separate the metadata from the product, and we cut the product in patches in a multi-grid. For instance, 200 by 200 patches, 100 by 100, 50 by 50. The size of the patch is a parameter as a data ingestion. Later, we generate visual data for operation because we use interactive operation. And synthetic aperture radar and multispectral data, they are not directly visualized on the screen. So we make this transformation like a quick look. But a quick look preserving the resolution and adapted for visualization. And from this, we extract descriptors on each of the patch. All this information, it is further structured in the data mining database, where we have tables for metadata, for the signal feature indexing the quick looks, and also we have dynamic tables which are containing the semantic, which is created by machine learning. So the operations we can perform are queries, so data mining, like grouping based on metadata content and semantic content which was created. So Earth observation extracted semantic, which was created in the CANDELA data mining tool. We have data mining, we have the active learning, the knowledge discovery, which it is an interactive process of machine learning combining support vector machine and Bayesian decision. This it's operating by like a dialogue. The user is indicating the samples he's searching, the type of land cover he's searching in his application, also indicating negative examples in such a way to separate better the classes. The system responds and show to the user what the system understood. And after 5, let's say 7 iteration, the system is learning and presenting the classes which have been extracted. So that is actually a short demonstration. It is a didactic demonstration. That is not the actual interface, graphical interface, or human-machine interface in CANDELA. I choose this demonstration because it fits in the screen for the presentation. The operation is identical. So in here, the user is giving positive examples, which are marked in green, so in upper part, and in red there are negative examples, so what the user is not willing to search for. So this query, it is on SAR for agriculture fields. So the user is willing to have agriculture fields with no vegetation, he marked in red areas of agriculture and bushes, and the system takes this training data set and is filtering again. On the bottom now there is a query which actually shows that the agriculture has been filtered, reducing the areas with trees or bushes. After another negative example, the class was understood, and now on the bottom we have agricultural fields with no vegetation. The next example shows a query for high buildings. The training is very fast. One sample is enough to query over the data. The next query, it's choosing build-up areas on the right side, marked in green. Again, very fast learning. And after training, the system is generating an index to the class which was selected, and the user is labeling them semantically, writing a label in the database. And from this point, the data It is semantically labeled and can be queried by SQL or other tools for data mining. We chose the active learning. So this is an example of query on semantics for the storage tanks. So this is a semantic query, give me storage tanks. As the system is searching the database, retrieves, presents a patch with a storage tank and indicates the products with all the metadata, location, time, where they have been found. So actually we choose the active learning for many reasons. So one reason it is in Earth observation, training data sets are very expensive. So reference ground truth data is extremely expensive, and even they are not available. Training data sets also, they depend a lot on the user interest on the application. So existing benchmark, which are now popular in literature, become to be popular in literature for deep learning, they are not always usable in application because they do not contain the classes of interest. In active learning, this process indicates what the user is searching for, looking for. The system understands and shows also positive and negative example. The user selects again what indicates the class as a target of line cover he's looking for. This process actually is a process of very fast learning. Fast learning, fast as time because it takes seconds, minutes. The interaction we have seen, it's real time as a user activity, but also is fast in the sense that the semantic level, the classification is obtained with very few training data sets. And also it generalizes fantastically. So our method actually it's generalizing about 3 orders of magnitude or more data compared with state-of-the-art active learning methods. And again, the number of samples for training, it's very, very small, tens of samples. This is very important because the user can verify the training data in such a way to very precisely classify the area he's of interest. So this was our intention. Also, the system is designed with human-machine interfaces, as we have seen, in such a way that the user, which is a non-expert, can operate it without knowledge in programming or SQL or let's say internal programming. So that's it's addressing a very broad class of users. So the tool can be operated in various modes. Can be operated as browsing, because on a given example, I browse all the area of interest, all the database for the project I'm working. I start with discovering classes. So it's a discovery, it's an analysis of the training data set, of the data set. There is definition of region of interest, because looking to, let's say, many large areas covered by Sentinel data is difficult to analyze visually or any other method, which are the objects structure which could be identified. And when this discovery phase is finished, the operator can go and generate level data. So these semantic labels, this classification, again, they are defined in the active learning process, and they reflect directly the user interest. The user can define any classes he found that is possible to be extracted from the data. So this was a part on data mining. This is some results on Sentinel-1 in Waddenzee in Netherlands. It is an area, one scene, on which have been defined 14 semantic labels, so number of classes which is extracted. It's adapted to the user hypothesis, to the user needs, and also the number of semantic classes is very large. And again, semantic classes are not cartographic, extracted from some training pre-labeled data. external to the system, they reflect the reality, the actual reality as a moment of the acquisition. This means it's possible to make to reactualize the cartography or detection of land cover structure or objects. On the upper part, there is the precision and recall. So we behave depends on the class. We are somewhere in between 80 and let's say almost 100% in precision of recovery of the classes. So this is an example on Sentinel-2 in the same way, operated interactively. So in here there are 11 semantic levels have been defined, and the precision recall figures have been depicted on the bottom right. In the data fusion, we are working on
Mihai, this is Jose. Sorry to interrupt you. I know that we have like 10 minutes more room because in principle the system was booked until 2:30. I really didn't want to interrupt you, but at least I would like to give 5 minutes to Bowie for the their slides. So
I conclude. Data fusion, we exploit the complementarity of the optical multispectral data and the SAR data. This complementarity could be, I skip the detail on implementation. They could, for instance, be alteration due to the cloud or complementarity in the signature, as are the images on the right side. It's clear that radar and optical, they detect different signature of the land cover objects. So we exploit this complementarity to have a better classification or to be able to classify areas where incomplete data, incomplete observation exist. The principles are the same as the data mining, is the same active learning, merging features, fusing features from both sensors. And these are some examples which have been obtained on the TerraSalix or Sentinel worldview, and we have now much more results on data fusion on Sentinel-1 for Sentinel-1 and Sentinel-2 for the use cases in CANDELA. I conclude on here that I don't go over the figures. There are too many numbers. Thank you. I hope that I was almost in time.
Thank you very much, Mihai. Yeah, as I said, the webinar was scheduled until it was foreseen to finish around this time, but I think we have room for 10 or 15 minutes more, and at least I would like to get 5 minutes for questions. So, Bowie, I will make you now presenter, so you can go with the semantic search and indexation slides, but please try to be fast, okay? Please let me know if you can take control of the screen because you are in the attendees list. I hope you can, but since you are not logging as panelist, I wasn't totally sure. Please let me know. If not, I can show the slides for you.
Hello. Hello. Can you see my screen?
Yes, please go ahead.
Yeah. So the idea behind semantic search is to integrate various data sources from in different formats such as JSON, files, TIFF, or GeoJSONs. For the Vinya use case, the main data sources are the chain detections and the land cover classification from our partner. And we have identified many auxiliary data, such as the weather forecast measure and the weather forecast newsletter, and also the administrative units and cadastral parcels, and the land cover. And so the auxiliary data may be useful and can explain the use case or the results of a partner. For example, the chain detection why it's a low chain or high chain in a certain area. And our system is composed of the two Docker. The first one is used to retrieve the data sources, process the data, and transform the data to semantic format. To do that, we have developed several special temporal ontology that model the one data sources. And next, we have defined several templates that are the mapping between our ontological models and the data source schema. And next, the second Docker is used to query and visualize the results. The Docker is composed of a web application interface with query triple store. The triple store is a specific database used for semantics data. And we have deployed on the script, the triplification script, and the template on Jupyter Hubter that I show you next. And here we have prepared two Jupyter notebooks for the hackathons. The first one is for triplifications, and the second one is for semantic query. So first we will show you the use case, the vanilla use case. The area of the use case is inside the T30 TYQ Sentinel-2 type. That is in Nouvelle-Aquitaine region of France. And here all the information about the type is contained on our semantic space. So I send a query to retrieve the information of the type, and I show it on the map. And next, I send another semantic query to retrieve all the villages inside the area. And I list here the first 20 village. And so you can click on each of them to see it on the map, right here. And for each village, we have several information such as population name, the NC number, or the area, where the NC number is the most important that you should remember. And we will use it next in the next step. And the third step is to download the cadastral parcel. And we must enter the NC number here to download the dataset. And next is for the simplification. And here I show you the context of our template. Here we define some mapping between our ontology and data source schema. And next we will launch the simplification process. So here we can see the village has almost 7,000 parcels, and there are triplified in 7 files. And next I show you the contents of semantic data. That are the output, where we have the information about the parcels, the number, the continent, the land cover, the geometry, and the village that belong to. And the next step is to upload the outputs That's our semantic data to our semantic base. And next, we will launch another triplication script for the chain detections. To save time, let's suppose that we have already the chain detections from our partner. And so we have the output, the semantic data, and here's a extract of the contents that we categorize the chain detection on 4 levels: no chain, low chain, middle chain, and high chains that are some percentage. And the final step is to upload the data to our semantic base. We can do the same way for other data sources such as NDVIs or vector measure. And for the second Jupyter notebook, we will query the result. Here, I make another semantic query to show the change occur in several villages. And we have the pairs of change, the name of the village, and the number of the parcels, and the percentage of change. And we can click on each row to show the village on the parcel pattern on the map. And we can do the same way to visualize the NDVI level. And here I show you another semantic query to retrieve weather forecast measure for the village. Here we have all information about rain, wind speed, the temperature, atmospheric pressure, humidities. And in the same time, we have developed a web application interface where we have 3 filters: a temporal filter, a semantic filter, and a spatial filter. And for semantic filter, that we categorize on chain level, NDVI level, or linear health email level. Here I choose low chain for semantic filter. And we can roll area on the map to retrieve all the chain occur on that zone. And when we click on a particular village, we can obtain a graph that contains weather measure and chain detection. The result of chain detection that we can see here, we have about 40% of low chain, and here is the humidities that is particularly low in that period. That is the period of frost, and we can see other measures like temperature that have a 4 chain in that period. And we can also switch to tabular mode for more detail about its data sources. So we have here the Sentinel metadata, the chain detection region, and we must have here the vector forecast also.
Okay, thank you very much, Bagui. I have to apologize a little bit for the attendees since we spent a bit more time than that needed, but at least I would like to give the possibility to attendees to maybe for 1 or 2 questions before definitely we have to finalize the webinar for today.
This is for me,
Okay, thank you a lot. So I don't know if we can answer quickly 1 or 2 questions. Sorry for that. In any case, As I said, both presentations from OpenEO and Candela will be made available. Definitely the one from Candela from our website, but also I guess we will discuss among the different projects that from the registration page we are able to also to make available the webinars. So I don't know if there is any comment from the attendees, and if not, probably we should finish here the webinar. I see still Alex and Jeroen in the call. I don't know if you have also any final remark from your side.
Yeah, thanks for presenting all of this. It was very interesting and a lot of nice applications. I was wondering a little bit about this very file-based approach of linking the data, and if this not would be nicer to also have something more data cube based there, and this would be maybe something where also an integration with OpenEO could be possible, basically, in order to use OpenEO as an intermediate layer for the data access, basically.
I had the same. I was thinking about similar things when looking at your previous presentation. Indeed, we have a task on our project exactly on researching on data cube solutions. Candela started a bit later than the others. We were running now for 18 months. So still we have more than 1 year for final things to be done. And the data cube thing, now that you mention it, is one still of the things that we are looking at. So definitely there it will be one possibility where to find commonalities and maybe as using as part of the preprocessing or the setup before running the change detection algorithms, where it basically remains the most of the research which is done in Candela. Possibly we can benefit from OpenEO or maybe some of the other projects as well. Yeah.
Okay, great. I think probably now we're going to be kicked out of this any second. But yeah, thanks for the answer.
Okay. So yes, I guess we should stop here. Once again, thanks to the attendees. I hope you at least got a quick overview of what you will find in more detail in Frascati. Let's keep in touch. You have there the project website. If you search also for Candela H 2020 in Twitter, you will find out very easily our Twitter account to stay informed about any updates on our website. So thank you, and let's keep in touch.